Hello, my name is Thomas Cohn, and I'm an undergraduate student at the University of Michigan. On behalf of my co-authors, Otis Chadwick Jenkins, Karthik Desingh, and Jen Zhang, and the Laboratory for Progress, I'm proud to present our work, TSBP, Tangent Space Belief Propagation for Manifold Learning. I'll begin with some background. We now have access to increasingly detailed sensor data in the form of high-resolution images, dense point clouds, motion capture information, tactile sensing, among other modalities. But this data is often high-dimensional, and that can present some intrinsic challenges. For example, some algorithms or problems quickly become intractable, including POMDPs, particle filters, and reinforcement learning. It's more difficult for robots to interface with humans through data visualization or robot teleoperation. And there are general challenges that appear, such as the sparsity of a dataset growing exponentially with its dimension, the Hughes phenomenon, where adding more features without adding more data can harm the accuracy of some machine learning algorithms, as well as problems with handling the bias variance trade-off or detecting outliers in a dataset. A common solution is dimensionality reduction. To put it simply, we try to reduce the dimension of the data while preserving latent information. This has been used successfully throughout the robotics world. For example, it's been used to understand motion capture data, to compare grasp trajectories, to find functional similarities in tool shape, and to learn kinematic models for articulated objects. As I said before, dimensionality reduction attempts to transform the data to a lower dimensional space while preserving latent information. This is traditionally done by trying to preserve pairwise similarities and dissimilarities within the data. One common method is principal components analysis, where the data is projected onto a subset of its principal components. Another common tool are autoencoders, which are a type of neural network that attempt to find a compressed feature representation for all of the data while minimizing reconstruction error. I'll be focusing specifically on manifold learning, where the data is modeled as lying along some manifold and we try to find a low-dimensional embedding. Intuitively, you can think of this as taking a high-dimensional surface and trying to flatten it out or unroll it. Most manifold learning algorithms begin with a nearest neighbor search. It's a common tool that's used to discover local structure. However, it can sometimes make false correspondences. In other words, it's short-circuited by false edges. These false edges can be caused by noisy or sparse data, or when distinct regions of the manifold pass close to one another. So the points that they connect are quite distant with respect to distance along the manifold, but they falsely appear to be highly similar. For example, consider this data taken from a spiral manifold. When we perform a nearest neighbor search, there are many false edges that connect different regions of the spiral. These false edges will lead to a poor embedding, so in order to produce an accurate embedding, we have to remove all of these false edges. Let's take a closer look at this kind of manifold. In this case, the blue and red points are from two different regions of the manifold, and there's a false edge connecting them. If we look at the tangent spaces, which are the black lines at each point, we can see that the false edge is almost perpendicular to them. They're very dissimilar. So if we can estimate the tangent spaces at each point, that can tell us which edges need to be removed. However, tangent spaces are estimated using local neighborhoods, so these points will have poor tangent space estimates. If we return to the ground truth tangent spaces, we can see that nearby points have similar tangent spaces. And in fact, this is true on manifolds in general. If two points are sufficiently near each other, they'll have approximately the same tangent space. We can use this information to help get a better estimate of our manifold tangents. We formulate tangent space estimation as inference on a Markov random field. For each point, we have a latent variable that represents its tangent space, and an observation which is obtained from a principal components analysis of its local neighborhood. Points which are adjacent in the neighborhood graph lead to adjacencies in the Markov random field. We then perform belief propagation, convergence resulting in our accurate tangent space estimates, and we use that information to remove all false edges. We then forward the denoised neighborhood graph to existing manifold learning algorithms, and that computes the embedding. Let's return to the spiral manifold example I brought up earlier. Once again, looking at the nearest neighbors graph, we can see many false edges connecting across the manifold. These in turn skew the tangent space estimates. However, when performing TSBP, we are able to obtain much more accurate tangent spaces, and this in turn allows us to prune away the false edges. Belief propagation is an iterative process, and we can actually see the convergence happening by the iterations. We begin by sampling from all possible tangent spaces, and then gradually refine our estimates through a message passing algorithm. Eventually, we achieve convergence, and then select the maximum likelihood estimate of each marginal distribution, and treat that as our final tangent space estimate. We can also numerically measure the error of our belief propagation algorithm by iteration. After just a few iterations, the maximum and mean error quickly improve beyond that of principal components analysis. We can also analyze the embeddings themselves. Because this is a one-dimensional manifold, we simply plot the original parameter used to generate the data versus the embedding parameter, and we expect a continuous monotonic relationship. The ideal embedding shown below is simply a linear relationship. For each algorithm, we will see that tangent space belief propagation leads to much higher accuracy than nearest neighbors. This is true with isomap, local tangent space alignment, Laplacian eigenmaps, and t-distributed stochastic neighbor embedding. We also compare to multidimensional scaling and an autoencoder, two dimensionality reduction methods that don't rely on nearest neighbors. It's clear that in every case, TSBP is the only reliable way to embed this data set. We also examine a so-called Swiss roll manifold, which is a common example used in manifold learning. Once again, nearest neighbors discovers many false edges connecting different regions of the manifold. However, tangent space belief propagation is able to successfully remove all of these false edges. In this case, our manifold is two-dimensional, so we can simply directly plot the embedding. We look for a rectangular embedding as shown below, with no overlaps in the data. Isomap shows the clearest improvement, where tangent space belief propagation allows it to produce an almost ideal embedding. With local tangent space alignment, the embedding still discards the width of the manifold. However, it no longer overlaps data from different regions of the manifold. The same is true of Laplacian eigenmaps and t-distributed stochastic neighbor embedding. Once again, multidimensional scaling and an autoencoder also fail to produce accurate embeddings. We also use TSBP as part of an object classification task using high-dimensional tactile data. Tactile sensing is very useful for intricate grasping and manipulation, and Sundaram et al. Built a scalable tactile glove that can gather detailed information from a human grasp. It contains a dense array of force sensors, generating very high-dimensional data, and then they used this data to perform object classification with a deep convolutional neural network. However, this neural network requires very large amounts of data, and we wanted to explore if we could still produce accurate object classifications without so much data. We used a Gaussian process classifier with an RBF kernel to perform our classification on a small subset of the training data. This kernel relies on the Euclidean metric, which performs very poorly in high-dimensional spaces, so dimensionality reduction is necessary. In this case, we use t-distributed stochastic neighbor embedding, or t-SNE for short. First, we consider the expected accuracy if we simply selected the class of the object at random. We then compare that with a Gaussian process classifier trained on the original data, and we see very little improvement, likely due to the high dimensionality. We also train a GPC on an embedding generated from ordinary t-SNE and nearest neighbors t-SNE. In both cases, we see poor performance as the false edges discovered lead to a poor embedding. Computing an autoencoder embedding does lead to slightly better results, and we get even better results if we use the deep CNN brought forward by Sundaram et al., although it still suffers from lack of data. The best results, however, the highest accuracy, come from a GPC trained on a tangent space belief propagation embedding. To ensure robustness of our results, we ran this experiment 100 times and averaged it. However, we've also plotted the results in a kernel density plot. As you can see, tangent space belief propagation consistently leads to the highest accuracy. So, to conclude, I've discussed how high-dimensional data is inherently difficult to work with, and brought forward manifold learning as one solution to this so-called curse of dimensionality. I've also described how sparse and noisy data can cause manifold learning to fail, and presented our algorithm TSBP. It makes manifold learning more robust by accurately estimating the tangent space at each point and using these tangents to identify false edges. After removing false edges, a denoised neighborhood graph is forwarded to a manifold learning algorithm, producing a much more accurate embedding. Thank you for your time.